Right, so I'm going to write the terms that have the highest exponent first, and I'm going to put it in what we call descending order. We wrote it twice in our notes, descending order. Get my sip of coffee, now we're ready. It would be a wonderful, wonderful, beautiful day for me if I were, once I have the floor, for you guys to take off your headphones without me asking you guys. Like I would, it'd be like a dream come true. Like try to do it before having me to say the same stuff like a broken record. I really appreciate you guys. So Vega's right. Standard form is rewriting the polynomial function that has the terms with the highest exponent first. This one first, this one second, and this one doesn't have a variable, so I put that one third. So standard form. So standard form. You're going to get some questions like this on assignment 14 on when you go to big ideas. Standard form is, watch me rewrite f of x. The function f of x, watch this. The function f is 4x to the third minus 2x squared. Look at it in descending order from biggest to smallest. Biggest exponent to smaller exponent. Minus 3. Here's standard form. We're rocking and rolling. It's really not that hard. Let's rearrange the polynomial. That's not rocket science. Notice how 4x to the third was positive, so I maintained it as positive. Negative 2x to the second, it's still negative. Make sure that you're aware of that. Okay, making sure that the signs of the terms are correct. All right, that's the first mission. Standard form. Look at part B. State the leading coefficient. Okay, the leading coefficient, I'll put LC for leading coefficient. How about that? Someone besides Vega. She's awake. She gave me the first situation. What would be the leading coefficient here of this polynomial based on yesterday's notes? You're awesome. 4. Coefficient, what does coefficient mean? If you forgot, go to Ray Bradbury, one of my favorite authors. By the way, speaking of Ray Bradbury, I was delighted that my daughter, she's 20 years old right now, I read her a Ray Bradbury book, and she asked me, hey, Dad, where's that Ray Bradbury book that we read together? I want to read it again. And there's nothing more delightful for a father, it's that she actually remembers one of the books, and she's actually reading it right now. I recommend Ray Bradbury, but I digress. Above Ray Bradbury is an expression poster. If you forget what coefficient means, it's the number in front of a variable. Look at the 9. It has coefficient around it. So the lead coefficient, did Gomez or Cortez say it? Thank you, Gomez. Is the coefficient with the highest exponent variable. So the 4 would be the lead coefficient. But notice, negative 2 is the coefficient of the x squared. But the lead one, the lead coefficient, is 4. Cool. So you only write the lead coefficient when it's in standard form. Keep that in mind for assignment 14. Moving right along. That's the second mission. The third mission, the degree of the polynomial. Somebody besides Gomez or Vega, what would be the degree? Don't make me cry. I already cried enough last night as the Dodgers lost. I don't need to cry anymore. Hit it, Castro. What's the degree of that polynomial? Oh, like type? No, just give me the degree, the number. Yeah. You said 3? Exactly. So degree is 3. Thank you. The degree is 3. Based on the degree, the type would be cubic, and that's what you're thinking of. This would be a cubic polynomial, but the degree is 3. Very nice. Question, that was number 1. First mission, standard form. Second mission was the lead coefficient. Third mission, the degree. The degree is just the highest exponent. Simple as that. No rocket science here. All right. No questions? Udav is texting. That's awesome. We're ready to rock and roll. Let's do it. I'm going to bring down number 2 right here in green. Let me rewrite number 2 in standard form because right now it's not in standard form. Terms with the highest exponents are all mixed up and jumbled together. They're out of order. So the term with the highest exponent would be the 5x to the 5th. I'm going to write that one first. So here we go. G of x, remember a function doesn't have to just be f of x. This is a function g of x is 5x to the 5th. Okay, now the term with the second highest. Here we go, negative 3x to the 4th. There's Camacho, I've been waiting for you. Minus 3x to the 4th. All right. Minus 6x to the 3rd. Standard form. I'll put SF for standard form. There's standard form. Okay. Leading coefficient. Somebody who hasn't answered. Someone who hasn't answered. Thank you. What is? 5. So the coefficient is the number in front of a variable, and the lead one would be the one in front of the highest variable, right? It'd be 5, huh? So lead coefficient 5. Thank you, Juarez and Ayala. Moving right along. The degree. This would be a degree 6, you say. 3, you say. 4, you say. You just look at the highest exponent. Degree 5. The highest exponent is always a degree, so that'd be the degree 5. Assignment 14 is pretty basic. I know Gomez already started it. It's just a lot of just, can you identify the degree? Can you identify the leading coefficient? It's very simple. This will be on the quiz tomorrow, by the way. I'll throw a polynomial function, ask you to put in a standard form, leading coefficient, and then degree. And I'll probably ask you for the type, too. What type is it? Is it cubic, quartic, quadratic? That's just a matter of like having your notes in front of you and like reading your own writing. It's not like high-level thinking. Really? Right, Gonzalez? All right. Bust this out. Remember, I gave this yesterday. We put that little table before we went to go talk about the FAFSA. Bust this out. I want to talk about this here. I'm going to play this day in history. Okay. So let me type in a function. I'm going to type in a polynomial function. Watch what happens here. Let me write 3x to the 5th, let's say. Plus 2x squared. Oops. Watch this. Plus 2x squared. Plus 6, say. Keep on putting plus here. All right. Okay, so there's a funky graph there, right? All these as I was typing in these coefficients, the coefficients and the exponents determine the behavior of the function, how it behaves. Typically, when we talk about behavior, we're talking about people. How does your little sister behave? Don't answer that. How does your parents behave? You ever do childcare? Your mom gives you duties to take care of your little brother and sister. What's their behavior like when they're alone with you versus when they're with their parents? Is it better or worse? Behavior, we typically talk about people. But functions behave a certain way too. If I start tinkering with the coefficient like 3, let's make the 3, watch me make the 3 6. Look what happens to the function, the way it behaves. Watch this. There's 6. Let me tinker with this coefficient. Let me make this a 7. Notice how the behavior changes based on those coefficients. Let me make the 6 a negative. How about this? So watch this. I'm going to make it a negative 6. Look at the behavior change. Something took place there. Let me erase the negative. You see what's going on. So once I start tinkering with coefficients and exponents, things change. The behavior changes. Now, Watch this. So right now you're not doing anything, you're not writing anything, now you're just paying attention. This function, notice if x gets bigger, so look at the x values as I put my index finger on the graph. Look at, if I keep going down, x is getting bigger. See, I'm at 1.31, 1.3, okay, 1.32 now, 1.35. X is getting bigger because I'm going this way on the x-axis, but the function is actually getting infinitely smaller, smaller and smaller. Now I'm at -8. Look at the y values, or I should say f of x values. Here's x, here's f of x. As x gets bigger, f of x gets smaller, bigger and bigger, smaller. In other words, more and more negative. So x is getting larger. As x gets larger, the function gets smaller. We call that the end behavior. The end behavior. Because notice, here's a function, okay? How is it behaving at the ends? As x goes that way, how is it behaving? And as x goes this way, how's the function behaving? Notice, if I go this way on the x-axis, so notice, if I go towards -infinity on the x, if I go that way on the x-axis, now the function is getting bigger. The farther I go here on the x-axis, I have some y value up there. Y value up there. The more I go on x this way on -infinity, the y value is going to be higher. So as x approaches bigger and bigger negative values, the function approaches bigger and bigger positive values, and vice versa. If I go this way, as x goes to bigger and bigger positive values, the function gets into bigger and bigger negative values. We call that end behavior. Now, this handout I gave you, go and take that out. You should have that in front of you. It turns out that there's actually patterns of end behavior. And this is what's in front of you right now. Mathematicians have found out patterns based on the leading coefficient and on the degree. So, if you have an odd degree, so what are some odd numbers? When I say the odd numbers, what comes to your mind? 3, 5, 1, 3, 5. So if the degree of the function is odd and the leading coefficient is positive, you're going to have this kind of situation. The function f of x will go towards -infinity. Look, it's going to go down this way as x goes more and more towards -infinity this way. So the more and more you go this way on x, the function will always go down if the degree is odd and the leading coefficient is positive. Let me do that. Let me see if that works on the one I did. No, just because you don't have to draw that, just if you want to. But what I'm going to do is I'm going to exemplify what that first case is. The degree is odd. Let me see if my degree was odd. Let me bust out was my degree odd? Was the degree of this polynomial odd? Yes, because look at 5. 5 is an odd number. The highest exponent is 5. It's odd. And was the leading coefficient positive? Leading coefficient is negative. It wasn't positive. But what if I make it positive? Look, I'm going to take away the negative. Now, look at, that's exactly what's going on. Notice how the function is going to go towards -infinity as x goes to -infinity. The more you go on x, -infinity, the y will go towards -infinity. The function will go towards -infinity. And the opposite, the other end, if x goes towards positive infinity, the function will go towards positive infinity. If, and here's a big if the degree is odd and the leading coefficient positive, this is always going to be the case. The function will go towards negative infinity, this is on your paper, as x approaches negative infinity. And what about the other end behavior? So we call it end behavior. As x approaches positive infinity, the function will go towards positive infinity, no matter what it is. Get that for me, Gomez? How about this one now? Look at the second situation. I'm going to make the degree odd, but I'm going to make the leading coefficient negative. Notice how the end behavior, what they need? Naheda? After this rule, Naheda, 5 minutes. So look what I'm going to do now. I'm going to make the degree, I'm going to keep it odd, but I'm going to make the leading coefficient negative. Now the end behavior will be opposite. Instead of this, it's going to be like this. So my arms represent the end behavior. Instead of like this, that was this case, now it's going to be like this. Just by me changing the lead coefficient to negative. Watch. Check it out. So I'm going to make the lead coefficient of 6, I'm going to make it negative, and watch it flip now. Right now, the end behavior is like this. Watch it do this. There's a negative. There it is. It flipped. So now, as x approaches positive infinity, as I go more and more here on x, bigger and bigger, it's going, so notice the x's are getting bigger and bigger. The f of x, the function, is getting infinitely smaller. It's approaching negative infinity downward. Negative infinity. Because it never ends. Third case. Watch the third case now. The third case, let me make the degree even and the lead coefficient positive. Now what are you going to see? You're going to see the end behavior is going up on the left side and up on the right side. You may have a bunch of little squigglies in between, but the end behavior, the way it behaves at the end, up and up. In other words, it's not going to be this way or this way, it's going to be both up. And then the last case is going to be both down, the end behaviors. So there's patterns that mathematicians have seen. So let me change my graph to a degree of even and a lead coefficient that's positive. Watch this. Watch what happens. Here's my graph. Let me change the degree to even number. I'm going to change it to the 6th power. Check it out. I'll change the exponent to 6. And I'll change the lead coefficient to positive. And there you have it. Look what you got. Look at the end behaviors now go up. At this end, it's going up. And at this end, it's going up. All because of this. The degree is even and the lead coefficient is positive. It's going to make both end behaviors going up. And last but not least, I'll keep it even, but now I'll make the lead coefficient negative. Now it's going to be, the end behaviors will be going down. Watch. So degree is even. Watch me make the 6 negative. Notice how both arms of the function are going to be going down. There they are. Look at how they go down now, just because of the lead coefficient. That's it. There's really hardly any notes for today. It's just a matter of understanding this table, the different situations, 1, 2, 3, and 4. Okay? We'll go over more of this tomorrow. I'm going to give you the rest of time to work on your assignments. Yes, Gomez? It would no longer be a polynomial function. That would be called a rational function. Good question. The ones we're working on right now is only polynomial functions, which is why there's that one question, remember? Yeah. Okay.